This is a lesson on phase change and latent heat in the Heat and Thermodynamics unit. Up until this point, we have seen what heat is and heat transfer methods, and we've also seen the results of heat transfer to a substance that results in temperature change. Sometimes heat is transferred to a substance and this results in a phase change. Transfer of heat can result in any number of physical changes, and when heat is absorbed or released, we can see on a molecular level in the substance, the molecules are gaining so much energy that they overcome their mutual attractions with one another and become freer to move about. Or the molecules are losing so much energy that the mutual attractive forces are overcome, and so they're no longer free to move about. So that's what happens in phase change, is this energy goes into either overcoming mutual attraction or heat is lost and these mutual attractions take over. Most substances have three distinct phases: gas, liquid, and solid. A gas at its temperature below its boiling point is called a vapor. And phase changes depend on temperature and pressure. We're going to see this in a little bit. So you're familiar with boiling and condensation, and with melting and freezing points. Phase changes occur at fixed temperature for a given substance at a given pressure. And you will need to determine whether the heat flow is into the object or out of the object. Any phase change results in an associated change in volume. Because these molecules are becoming more condensed and attracted to one another, or less condensed and freer to move about, you will see the volume change accordingly. Looking at particulars of phase change, there's three different processes for phase change. The first is from a solid to a liquid, or a liquid to a solid. If we go from a solid to a liquid, this is melting. And energy goes into melting. It takes energy to overcome these bonds, and these molecules become more free and more energetic. If we take energy away from a fluid, we freeze it and it becomes a solid. Vaporization is when we go from a liquid to a gas or a gas to a liquid. You can see I have a liquid here. If we put energy in, those molecules are more free to move about. If we have a gas and we take energy away, this is called condensation, we get a liquid in return. The last type of phase change is sublimation, when we go from a solid to a gas, right? Directly from a solid to a gas, or from a gas to a solid. And an example of that, if we go from a solid to a gas, that's like dry ice. There's just a solid, and that solid goes into a gas, into the air. Or if we take a gas and then freeze it, that's called sublimation as well, from gas to solid. And an example of that is when you freeze dry something. One of the ways that we represent phase change is with a pressure-temperature graph. So this is what we call a phase diagram, and notice that this phase diagram is for water. Each substance will have its own phase diagram. What you see on the phase diagram is three distinct regions in here, three distinct ones. There's S for solid. In this region, it's a solid. Over here is a liquid. We can see that there's a liquid region here. And then over on this side is V for gas or vapor, okay? And what we see is along any of these lines is when a phase change happens. Okay, so if we look at 100 degrees at 1 atmosphere of pressure, we know that water will go from a liquid to a vapor. It will go from liquid water to steam. Okay, so all along this line, actually, we can get water to go from steam at a smaller temperature if we lower the pressure, or we can cause water to not become steam if we raise the temperature. Water won't become steam until a higher pressure if you are at a higher temperature. The critical point is the temperature above which a liquid cannot exist. So when we look at this here, above this temperature, Regardless of the pressure, you will not be able to get liquid water out into a system. It will only be a gas of water. Another point on here that is important is the triple point. The triple point down here is the pressure and temperature at which a substance exists in equilibrium as a solid and a liquid and a gas. You can see that's where all three of these lines converge, is right here at that point. So it will be a solid and a liquid and a gas at 0.01 degrees Celsius and 0.006 atmospheres of pressure. All three will exist there. This line here is from solid to vapor, that's sublimation, and this line here is from solid to liquid. This is melting or freezing in here. So that is a PT diagram. I know there's a lot of information here, and getting used to reading these is a fine skill, so I will have some practice on this. Another diagram important for phase changes is the PV diagram, pressure, volume, and note that both of these are for water as well. These lines along here are what we call isotherms. All along this line, it is a single temperature T5, which is larger than a single temperature T4, which is larger than the other temperatures here. If I look at a small enough temperature, you can see that water will be a liquid for a certain region. In this region, it says the liquid vapor equilibrium region. So in this region, it will be changing from a liquid to a vapor in this region. Both will exist at the same time. We can get the substance to become a vapor regardless of the temperature because we're at a high enough volume and a low enough pressure. On this graph over here, you can see the critical point again. Remember, the critical point is the temperature at which any other temperature there will be a gas, okay? Above that temperature, it's only a gas. Below that temperature, we can see that it will take on liquid and vapor as well. Since each of these lines is an isotherm, notice that when the substance water is changing from a liquid to vapor or vapor to liquid, that happens at constant pressure and at constant temperature, but the volume is changing. Of course, when water goes to steam, it's going to have a larger volume than when it started. But also, I want to note that this is going to happen at constant pressure, and it's an isotherm. This is at constant temperature. Let's answer a few questions regarding these diagrams. The first question here says, a pressure cooker contains water and steam in equilibrium at a pressure greater than atmospheric pressure. How does this greater pressure increase the cooking speed? So here's the pressure temperature diagram, the phase diagram for water here. And let's think about water changing to steam or boiling. Okay, if I look at boiling water at 1 atmosphere, it will change from liquid to vapor at 1 atmosphere at 100 degrees. So if it's just boiling on your stove, it will change to gas, and you're kind of losing that heat. Whatever heat you're putting into your pot, it's going into changing the water from a liquid to a vapor rather than going into your food. However, if I raise the pressure, and I'm going to extend this temperature line up and show you this region here. If I raise the pressure above 1 atmosphere, I'm in the region here where I have high pressure and temperature greater than 100 degrees, and I still have water as a liquid. Water is still a liquid in here, right? So instead of the heat from the pot going in and making the water turn to a vapor, what happens is it goes in and makes the water hotter, and then all of that heat goes into the food instead of into steam. So because the heat is staying in the pot, it will make the cooking speed faster because the food is receiving the heat faster. Part B says, explain why a cup of water or soda with ice cubes stays at 0 degrees even on a hot summer day. So this has to do with an isotherm, and I'm going to bring you back to the feature of the graph here where I have the liquid vapor region. Okay, and remember, each one of these red lines is an isotherm. When water is changing from a liquid to a vapor, or we can think of it also from changing to a solid to a liquid, that will happen over an isotherm. Okay, and so the pressure will be constant, the volume's changing. I'm okay with the volume changing, but what this is saying is it happens over constant temperature as well. So if it is ice to water or water to ice, this will happen at 0 degrees Celsius. It will stay at 0 degrees Celsius. As long as there's ice there, the ice will be at 0 degrees, and it will be changing to water at a constant temperature of 0 degrees Celsius. So that's why ice stays at 0 degrees even on a hot summer day. That melting process is still going on, and the heat that's coming from the water is going into melting the ice rather than changing the temperature of the liquid. Here's another diagram, and we're going to note that there's a temperature on the vertical axis and heat on the other, heat per unit mass. So as we add heat, as we add more and more and more heat, we look at the temperature. And again, what you see on this diagram is that phase change is an isothermal process. Phase changes happen at constant temperature. So I can have ice and I can warm ice up to 0 degrees, but as soon as ice gets to 0 degrees, it will stay at 0 degrees and change into water, and you will have a mixture of water and ice at that point. After all of the ice melts, we can go into raising the temperature of the water. So as the water gains heat, right, we're adding heat, the water will become warmer and warmer in temperature until it gets to boiling, at which point the water will become steam. So any heat coming into the system will go into freeing those molecules from being bound, mutually attracted to one another, to being free as steam molecules. Once all of that water has been changed to steam, we can then raise the temperature of steam. Another feature of this graph that I want to show you is to look at the amount of heat to change some amount of water from ice to water. All right, so that's the amount. It takes this much heat in order to melt the ice. The same amount of water now, if I want to change it to steam, takes this much energy to change it to steam. So you can see that it takes way more energy to make something a gas than it does to make it a liquid from a solid. Okay, so these are features of this graph. Let's talk about the concept of latent heat. Latent means hidden. And what you may have seen on the graphs before that was kind of hidden to you is that the energy of phase is stored as internal energy, as the mutual attractive forces between the molecules in that. So when you look at ice, the energy is saved in the bonds between the water molecules in the ice. So it's hidden. And what latent heat is the amount of heat required to cause a phase change for a substance. And notice that this is normalized per kilogram. So it takes so many joules per kilogram in order to cause something to become a liquid, or to become a solid, or it takes a release of so much energy to become a liquid or to become a gas. Solid to liquid is given by the latent heat of fusion. We call that solid liquid. Okay, so if you're dealing with ice to water or water to ice, you would look at the heat of fusion, the latent heat of fusion, and you can see those values there. If you're looking at from liquid to gas or gas to liquid, vice versa, you would be looking at the latent heat of vaporization, and that's a different number. Remember on the graph on the slide before, it takes way more energy in order to vaporize a substance than it does to melt it into a liquid. It takes way more energy. Okay, so you will be using this table occasionally. What I'm going to highlight here is water. Water, the latent heat of fusion for water is 3.33 times 10 to the 5th joules per kilogram. The latent heat of vaporization is 2.26 times 10 to the 6th joules per kilogram. So we have a whole power of 10 increase there. And it takes more heat to make steam. Let's get into quantifying these ideas and look at phase change in latent heat with an equation. We have an amount of heat. The amount of energy depends on the substance changing phase as well as the nature of the substance. So we have an amount of substance here, the mass of the substance, and then we also have the latent heat. And this could be a latent heat of vaporization or a latent heat of fusion depending on the problem. The units, of course, here is joules. This will be kilograms, and on the slide before we saw that this is joules per kilogram. Of course, this makes sense. So the units aren't too bad on this equation. This is a pretty simple equation. Let's put this equation to work in an example. I have energy in a cloud. This is a really cool example. The energy released from condensation in thunderstorms can be very large. So if you imagine all of the water vapor in the air in the form of clouds, and that condenses and then falls as rain. All of the energy of the molecules moving around in the air is taken away, and they become condensed into rain. So calculate the energy released into the atmosphere after a small storm of radius 1 kilometer, assuming that 1 centimeter of rain is precipitated uniformly over this area. So I'm going to imagine like there's some sort of cloud, and it says that it has a radius of 1 kilometers, which I know is 1,000 meters. I'm going to put this in SI. And so all of the water vapor in here gets condensed and it falls as rain. So what I have underneath here is we're going to have a small cylinder of rainwater that is 1 centimeter tall. Okay, and it has the same radius. So we have a cylinder of rainwater. If I want to compute the heat that is released in this process from a cloud, from water gas to water liquid, I want to take the mass of the liquid and then the latent heat of vaporization. Remember, this is latent heat of vaporization when we condense from a gas to a liquid. So I'm going to put vaporization here, and I want the mass of the water. Well, I have a volume of water, right? This is a volume of water. V water has to equal the volume of a cylinder, pi times r squared times h, right? I take the area of the base and then I multiply by the height. So I have pi r squared, and then the height is h. So I have a volume of water. I need a mass of water. Well, I know how to relate mass and volume. Mass equals density times volume, and I know the density of water is 1,000 kilograms per meter cubed. So I can calculate the mass of the water. The latent heat of vaporization for water is 2.26 times 10 to the 6 kilograms joules per kilogram. Okay, so when I write this equation out, I'm going to get Q equals rho water, V of the water, times the latent heat of vaporization. So let's get all this in here. Rho water is 1,000 kilograms per meter cubed. The volume of the water is going to be pi times r squared, which I know is 1,000 squared. We have 1,000 squared. And then the height is 1 centimeter, right? This is the height of water, 1 centimeter. So I'm going to put 0.01 meters in here. So that gives us a meter cubed, and a meter cubed, I have kilograms left over. I'm going to write in here the latent heat of vaporization, 2.26 times 10 to the 6 joules per kilogram. The kilograms cancel with the kilograms. I'm left with joules. So this becomes 7.1 times 10 to the 13th joules. 10 to the 13th, that seems like a lot. Okay. Let's remember that it wants the amount of energy in calories. If I think in calories, I have a little bit more reference point. I'm familiar with what calories are. We're going to remember that there are 4.186 joules in 1 little C calorie, and that there's 1,000 little C calories in 1 big C calorie. When I run all this through the calculator, this gives me 1.686 times 10 to the 6th big C calories. Okay, that is a lot of calories. 10 to the 10th, that's a huge amount because 10 to the 9th is a billion, right? That's a billion. So we're over at a billion calories stored in a rain cloud. That's a kilometer in radius. And if you're interested, we've done problems where you had like 250 calorie candy bars or desserts. If we divide this into desserts, how many desserts could you eat? This is 76.8 billion million desserts, which is a lot of desserts, right? That's a lot of candy bars in the sky. This is an ideal exemplification of how water stores so much energy. Also, it's an exemplification of our hydrosphere, where energy is transferred from different places on the earth through clouds and water in the air. It can store a lot of energy, moves the energy around on the planet, and weather is one of the primary ways that energy is transferred on the surface of the planet from one region of the earth to another. Pretty cool stuff. I have another example here called cooling your drink. You use 5 ice cubes to chill a soda with mass 250 grams at 20 degrees Celsius, so about room temperature. The ice is at 0 degrees and each ice cube has a mass of 6 grams. Assume that the soda is kept in a foam container so that heat loss can be ignored. Assume the soda has the same heat capacity as water. Find the final temperature when all the ice is melted. Okay, so in order to do this problem, this is conservation of energy. I have energy moving around. Ice is receiving energy and the soda is losing energy. And remember, we did this on a problem before. The change in energy for the whole system is 0 for the system. And so what we're going to see is that the Q gained by one part of the system plus the Q lost from the other part of the system will equal 0. And so we get Q gained has to equal negative Q lost. Okay, and in this situation, the water is losing heat, right? Over on this side, this will be the water. And over on the other side, the ice is gaining heat. The ice will melt. And then also there's going to be a final temperature. So when I think about this ice, the ice will first melt. Once it melts, it will heat up. So there's going to be 2 terms over here on the gain side for the ice. So let's account for this. We're going to have Q for melting the ice plus Q for heating the ice, and that has to equal negative Q for Q cooling the water over on this side. Okay, so I'm getting this together, and I know each one of these Q's is different. Q melt will equal the mass of the ice times the latent heat of fusion for ice and water. Okay, the latent heat of fusion for ice and water is 3.33 times 10 to the 5th joules per kilogram. You can get that off the chart that I showed a little bit earlier. Then we have to heat up the ice that is now water, right? It's now water and it still needs to get heated up. So Q heat, I'll call that, is going to be mass of the ice, specific heat of water, times the change in temperature for this ice from 0 to whatever the final temperature is. Okay. Over on the other side is the water. Q cool for the water. There's some mass of water or soda here, what we're dealing with. Instead of water, this is soda. I took it as water because it says assume the soda has the same heat capacity as water. So that's why I was writing water here. So this will be mass of the soda, specific heat of the water, delta T for the soda. Okay, so that's what's going on here. The soda is going to end up with a lower temperature, so overall this term will be negative, and I have a negative out here, and so it'll become positive overall. So I can take care of that. So I have all the terms here, and I'm going to put them all into the equation so you can see this a little bit more at work. Mass of the ice, latent heat of fusion for ice water, so that's Q melt. I'm going to add on Q heat, which I know is mass of the ice, C water, delta T ice, which I'm going to say T final minus T initial for the ice is 0. Remember the ice is 0. I'm just going to plug in 0 there because that's going to get rid of some of my, that's going to get rid of a term. Over on the other side, I'm going to have negative soda, C water. I'm going to do T final minus T initial soda. T initial soda was 20. Okay, so we have a mass here and a mass here. Mass ice equals 5 times 6 grams, which equals 30 grams. And then the mass of the water equals 250 grams. Okay, so I have an equation going on. They ask me to solve for the final temperature, and you can see that the final temperature is in a couple of terms here, so I'm going to have to do some algebra to isolate it. One thing I'm going to do is divide everything by CW. Let's do that. Divide everything by CW. So if I divide by CW everywhere, CW, then I'll cancel there, and I'll do a CW here, and that'll stay. I'm also going to divide by an M ice. That'll let me get rid of it on this side and then only have it in one term. So M ice here, those cancel, and I'm left with LF over CW. Those cancel there. And then I have M ice there with M soda. Okay, so I'm simplifying. I'm doing a lot of things in one step. So let's see, what do I get? I get LF over CW. I get LF over CW plus T final. That simplified easy. Equals. And I'm going to distribute this and take the negative sign into account. M soda over M ice, T initial soda, minus M soda over M ice, T final. Okay, again, I'm isolating down for T final. I need to get T final on one side and everything else on the other. So I'm going to do a step of algebra. I'm going to bring this term over here. I'm going to take this term over here. Okay, I'm going to make some space here. I get T final plus M soda over M ice, T final. That's this term moved over to that side. That has to equal mass of the soda over mass of the ice times the initial temperature of the soda minus LF over CW. So this is the latent heat of fusion over the specific heat of water. Okay, so there's implied a 1 here, and I can factor TF, so I get TF 1 plus mass of the soda over mass of the ice equals this stuff. I'm going to divide on both sides. So I get divided by 1 plus mass soda over mass ice, and then that gets rid of those terms. I get this equation here. You can forget that for a second. This equation here, I'm running out of space, so I'm doing some safe spacing here. Mass of the soda over mass of the ice. Well, they're both in grams. Technically, I should convert them to kilograms because I have latent heat of fusion and the specific heat in here in kilograms. But I'm doing a ratio of these two, so if I convert them, it's going to get lost. So I'm just going to do a ratio of the grams. So I have 250 over 30 times the initial temperature of the soda, which I know is 20. Initial temperature of soda. I'm going to subtract off LF over CW. So I have 3.33 times 10 to the 5th. And I'm going to divide that by the specific heat of water, which I know is 4,186 joules per kilogram. I'm going to divide that by this term here, 1 plus the 250 over 30. When I run this through the calculator, I get 9.3338 degrees, and this will be in degrees Celsius. Okay, so the final temperature, and when I look at this, does this make sense? I have 0-degree ice, and I only have 30 grams of it, and I'm adding it to 250 grams of 20-degree soda. And it's going to take a lot of heat in order to melt that ice, so that heat that goes from the water will go substantially into melting the ice, and then some of it will go into heating it up. So I'm not surprised that this final temperature is closer to 0 degrees rather than 20 degrees, because we lost a lot of heat to melting the ice rather than heating up the water in the system.